Okay, so then welcome to lecture 6. So today we will be talking about oscillators. So what are oscillators? Oscillators are things that make oscillations. What are oscillations? Oscillations are things going up and down and up and down. Again, like a clock, for example. Why would you have these things? So why are these things useful? For example, we heard last week already that oscillators, for example, in your computers, in your phones, are useful to ease up computation. Even though computation gets more and more asynchronous, as we also heard last week, many of the things are still synchronous. And you use kind of the time information to say, oh, now I have to calculate some value, which can then be used in the next cycle by the next stage. And this can be done without explicitly giving the signal. Like there would be an implicit time signal. It's also good whenever you need to schedule something. If you need to remember to do something every X hours, every X minutes, every X days, it's a good thing that you have a watch, for example, where you can set an alarm so that it wakes you up in, let's say, 8 hours after you went to sleep. So whenever you need to do something regularly, having an oscillator can help you wake up or start the process further down the line. Some examples. Of course, here thinking about biological examples. For example, the most striking one might be the circadian rhythm. You have it, other animals do. Like you wake up approximately your inner clock repeats approximately every 24, 25 hours, even without looking at the sun. Now, for example, there's also like a cell cycle rhythm that you can think of. Even if you think about bacteria, they don't really have a circadian rhythm per se, but they do duplicate in approximately regular intervals. So there's some things that happen over and over in the population of your bacteria, which is just cell duplication. Another one which we will look at today are like synthetic clocks, which you can also do in bacteria. Okay, so this is kind of oscillators Y and some examples that already exist. How would we implement them in biology? What is needed for it? And we will look at some like design principles that absolutely need to be there, both just qualitatively and quantitatively in the mathematical models. So let's say requirements. What do we absolutely need to have to produce oscillators? And this we know already some things from last week. Last week, you guys have heard about feed-forward systems and coherent and incoherent feed-forward systems. With incoherent feed-forward, I might just write FF for feed-forward, and incoherent. Let's do a small matrix. So your system might be coherent, might be incoherent. It might be feed-forward, or it might be feedback. Okay? So for example, if we have, let's say, 3 genes, and we have something like this. Gene X1 upregulates gene X2, which upregulates gene X3. And then there's another like path, which is also feed-forward, going in the same direction, which is X1 feeding, positively feeding X3. So what we say, can this thing oscillate? What will happen if we run the system? Yeah, exactly. Yeah, exactly. So x1 will go to some point, which will then regulate x2, which then will go to some point, and then x1 and x2 have some approximately stable point, and then x3 will follow suit. No, absolutely no oscillations. So what about an incoherent feed-forward loop? Let's say we have something like this. Again, x1 positively upregulates x2, which positively upregulates x3, but then we have some incoherence. Let's say now x1 represses x3. What happens here? Just to say, no oscillation here. We saw that last week. That is, yeah. 100%. Those are the two possibilities. There you can have something approaching an oscillation, or one oscillation, but not a sustained oscillation. Absolutely. So the best thing that you can hope for is something like this. But of course, what will happen is that x1, since it doesn't have any inputs, it will just go to some value, eventually, some steady state. And then x2, it only has like a steady state input. x1 will also go to some steady state. And then now x3 has two inputs, but they can be assumed to be in steady state. So this also will eventually go to some steady state. So maybe one oscillation, one pulse, but no sustained oscillations. Also no here. What about coherent feedback? So both these tell us already feed forward will not cut it. We will need to feed something back. For example, this is coherent, everything's upregulating. Can this have oscillations or not? Yeah, exactly. So more or less all three of them, that we go to their highest state that they can sustain, because we only have this upregulation. So it will go up at some point. It can't go to infinity because it's a biological or physical system. It doesn't have infinite resources. So everything will go up and then stabilize at some point, even though we have feedback. Also, no. So that leaves us with incoherent feedback. This is what we need to focus on. And this is what we will focus on in the rest of this lecture, of course. Yeah. You count the same way, but just...
Yeah, but now there's only one way to go from, let's say, x1 to x3.
So from x1 to x1, there are many ways. It's just like the path of length 0, path of length 3, path of length 6, and so on. Okay. Of course, you only have to compare 0 and 3, really. Okay. Okay. So we already know kind of how our circuits should look like. They have to have feedback. No way around that. They have to have some incoherence. So I think 2 weeks ago, we analyzed a very simple incoherent feedback cycle. Called this negative autoregulation. We saw that in some relative time scale, this speeds up the reaction time of your system. Let's see whether it can oscillate. So let's put down a mathematical model for this. We had something like this in the past. So let's say we have here, let's say even a Hill function that downregulates in x itself, that downregulates your gene. So if x goes to infinity, this term disappears. And then, of course, there's the degradation term. Okay. Now, can this oscillate? This is now an ordinary differential equation. Can this give you like a sine or a cosine or whatever repeating pattern as a solution? Maybe it would make it easier if I generalize the problem. Let's put any function f here. Of course, this already suggests that it's impossible because it doesn't even matter what the function is. Let's say this is time. The solution of whatever of this ordinary differential equation, either in this form or the general form of x. And let's say this is x. And let's say you are able to produce some periodic pattern here. Let's say it was possible. Then you can pick any intermediate point here. Let's say x0. And look at these points here. They all have the same x. Let's call it x0. And now, of course, we can ask the question. Let's say this is t1. Ask the question, what is tx at t1 dt? We know what it is. Because we do have the differential equation, this has to be f of x0. And we also know it's positive. By the same token, it's also strictly negative. Because the derivative only depends on the state, nothing else. So if you follow this reasoning, you will get something like 0 is smaller than 0, which is, of course, a very clear contradiction. You can't do it. One-dimensional systems, ODEs, cannot oscillate. Not possible. OK, so what about 2D systems? So this was 1D, no oscillations ever. What about 2D? Do you know two-dimensional differential equations that do oscillate? Let's write dx dt, dy dt. There's a very famous differential equation, not because it has a name, but it's very basic, and it gives you like very clear oscillations. Let's say dx gives minus y, and dy dt gives x, plus x. You know two functions, x and y, that fulfill this? Sine and cosine, exactly. So you can put x of t equal to the cosine of t. You can put y of t to the sine of t. Yep. OK. And of course, like it depends on the initial configuration here. So the initial value here, this will be, you can have this like, let's say you can multiply this by any number, and it will stay a solution depending, of course, on the initial value. Let's paint a picture here. And I won't put the picture of cosines and sines, you know how they look like. But let's look at this in xy space. Okay. Now whenever I draw something, I draw with respect to time. So first point here is time 0. And then I let t evolve. And what happens here, of course, with sine and cosine is it goes in a perfect circle. Let's say for a equal to 1, it does that. And for a equal to whatever, 1.5, we'll do something like this. And for a different a still, let's say a smaller one, do something like this. And of course, here's the point 0, 0. Okay? So what this tells us is it oscillates completely. This ODE oscillates completely wherever you put your finger, you let it run. If it's not in the origin, we start to oscillate perfectly in the circle. This is something that might not be what you want. What you might want, and I'm proposing this to you, is something that's called a limit cycle. So what is a limit cycle? It is, of course, let's say in the xy space. It is a cycle. Doesn't have to be a circle. Some cycle we do. With the property that first, if you start in the cycle, you stay in the cycle. You go round and round. But if you start a bit outside, you will converge to it. Maybe even below here a bit. Converge to it, not completely onto the cycle, but very close, and closer and closer and closer. Why is that something you might want? This is some sort of robustness. This has some inherent frequency, as opposed to our sines and cosines, which are a given amplitude which the sines and cosines do not have. Okay. And you can show actually. So if this is what we want, if limit cycles are what we want, we can ask the question, what do we need for limit cycles? And actually you can show that you do need nonlinear systems, nonlinearity. Which is good because most of our systems that we analyzed have been quite nonlinear. Because you can show, whenever you can have oscillations in a linear system, you have this almost too perfect oscillations where you just scale your whole system and you're still on a cycle. Okay. And then, so you do need nonlinearity, but then there's the question like, how do you find these? And this is something that's called stability analysis, or let's say linear stability analysis. There's a slight contradiction there, but it won't be in a minute. Which is just you linearize your system around a point here. So you might see this limit cycle, and you might think of all the different trajectories of your dynamical system that you can have here. So you go here, you go here. And if you follow all of these around, you will find that in the middle there has to be a fixed point. Somehow you can't cram all these trajectories in a coherent fashion in the middle without having a fixed point. So you will have a fixed point here. Let's say x0 now can be multidimensional. And then what you will do is you linearize your whole system around this point. And how you do this is by computing a matrix that's called the Jacobian. around this point. And then once you have this matrix, then you're back in a linear system locally, because doing derivatives is a local business. And then you need to have oscillations locally in your now linearized Jacobian system, which then gives you a chance of having an oscillation towards a limit cycle outside. OK, so how do you do that? So we would like to write something, let's say dx by dt is our differential equation, and now x can be like x can live in a multi-dimensional space. So it might be x, y's, and z's, and whatever. OK, and this of course is f of x, and now you're linear approximating this f of x around our fixed point 0. So this might be close to being x0 or f of x0, which is the same thing because it's a fixed point. And then you have this Jacobian f of x, so x of x0 times x minus x0 plus some higher order terms. And this is just the derivative. So the Jacobian of x, of f, is just the derivative of your function f, which now is a multidimensional function from n input variables to n output variables. So jf of x will be an n times n matrix, where here in the first entry you might have df1 by dx1 and df1 by dx2 and so on in both dimensions. This is just a linearization of your function f. And then this, given that this now is a matrix, you can linearly analyze this linear system, which you do by calculating eigenvalues. If you're not too familiar with them, some of you are, I guess, we added a small primer about how to calculate eigenvalues on the website. And if you look at these eigenvalues, you see the following rules appearing. So eigenvalues can be, even though this is a real matrix, so only real entries, it can have complex eigenvalues. So your eigenvalues will be of the form, let's say, lambda is a plus I times b, where I is the imaginary unit. And we have some rules. So if b is equal to 0 for all of your eigenvalues, you will have multiple of them, of course, then you can't have oscillations. What will happen there is only you converge towards the fixed point linearly even, and that's it. Now, if you have a non-zero imaginary part, you do have a few possibilities. So this allows you to have some oscillation here in the complex plane, but then it depends on A what really happens. So if A is smaller than 1, smaller than 0, excuse me, if you have negative real part, then you might oscillate around your fixed point, but you converge towards the fixed point. So not converging outward towards the limit cycle, you just converge on the fixed point. Converge here. If A is bigger than 0, then you might have a chance of hitting a limit cycle. Because what that tells you is that locally, you're doing some oscillations around the fixed point, and you're pushing outwards. Maybe this outwards will be a limit cycle, maybe it won't. It depends on what we see there. And a equal to 0, you won't be you might still have a limit cycle. It depends a bit on the rest of the system there as well. But you have here like a pure oscillation as we had with sine and cosine. This 2D system with sine and cosine, of course, had b not equal to 0 and a equal to 0. Only a purely imaginary eigenvalue. Okay. I might stop here for questions if you have them. And then in the rest of this lecture, we'll go over what's called the repressilator, which is an ingenious, like, synthetic biology design that really has an oscillatory behavior in bacteria. But do you guys have any questions about what we discussed up until now? No? So we need to have some feedback, we need to have some incoherence. Once we have that, we have to look at the ODE formulation of our system to see what's up. If we want to have limit cycles, first of all, we do need to have a nonlinear f. To analyze whether there is a chance of a limit cycle, we still linearize around the fixed point, which can be inside here. And then it depends on the real and imaginary parts of these eigenvalues to see whether we have a chance of a limit cycle, whether we oscillate and we push outwards towards the limit cycle. Okay. And then let's look at what's called the repressilator. The repressilator has two qualities to it. The first one, it's an oscillator. The second one, that's built by repression. This is an incoherent feedback cycle. So if you go around from x1 to x1, you have an odd number of repressions. So it kind of goes against the zero length path here as well. Okay. So why do we have that? So we already seen that at least in a naive protein-only modeling of a one-dimensional system, it can't oscillate. I think in this problem session, there's one problem where you have mathematically a two-dimensional system by including the mRNA and the protein. And you will see whether that can oscillate. In principle, you could have a x1, x2, like just a two-dimensional system, oscillate a priori. You can also check out whether that works. But one thing that we do know is if we have a two-dimensional system, it can't be symmetric. So if we have x1 and x2, if we have both of them be activations, then that's not incoherent. If you have both of them be repressors, then that's not incoherent either. So the easiest, so the smallest symmetric system that you can think of that can oscillate is x1, x2, x3, three-dimensional with three repressors. Okay. It turns out that this works. That's what, again, one of the two landmark circuits that started the synthetic biology really as a a prominent subject like 25 years ago. The other was the toggle switch. Yes?
I have a question.
Yes.
Can you go over the coherent and incoherent terminology once?
Yes, yes. So whenever we have like a diagram like this, where we have multiple genes and we have either activation by an arrow like this or repression by an arrow like this, then you can see whether our diagram is coherent or it's incoherent. And the rule is you go around different paths from one gene to another, and you count how many repressors you have. And if it's the same parity, so either both of them odd or both of them even, then you're coherent. If not, then you're incoherent, for example. So here again, this is coherent because from x1, you can only go back to x, so you can only go back to x2 with odd number of repressors, to x1 only with an even number of repressors. But you could have something like this. So x1 goes to x2, which represses x3, and x1 activates x3. So here, from x1 to x3 on the lower path, we have 0 repressors, so an even number of repressors. On the top path, we have an odd number. What this means is that kind of the lower path wants x3 to go up, and the upper path wants x3 to go down. And that's the incoherence. Yeah, thanks for the question. Okay, yeah, and of course here, the easiest system that might oscillate a priori, that's symmetric, is this 3-gene system. Let's write down an ODE for that. Let's linearize it after. Let's look at the eigenvalues. Let's do this whole linear stability analysis for the example of this repressilator. Of course, this will be very symmetric, so we're only going to discuss the first one. We, of course, always have the degradation term. Then here, we have a repression term. We already had that on the blackboard today when we discussed autoregulation. But now it's not x1 that regulates itself. For x1, it's x3 that regulates x1. If x3 is high, then x1 should get low. And here, or here, this is symmetric. So x2 is regulated by x1. And x3 is regulated by x2. So immediately made one very important simplifying assumption. It's that all the parameters here are symmetric as well, which is, in reality, it's not true. But for simplicity here, for mathematical simplicity here, let's assume that the gammas are the same, and the betas are the same, and the k and the n's are all the same for all 3 different genes. So this is a real hypothesis. Once you have that, you can go a bit further and kind of tweak your system a bit to make it a bit simpler, which is, first of all, you can remove the gammas here by adjusting the time scale. You can remove the k's here, again, by adjusting the scale. This, of course, will change the betas here quite a bit. But let's say we do all these transformations, and we know their effect on beta. Now, this is a different system. Doesn't have the same beta anymore. Doesn't have the same time scale anymore. Doesn't have the same scale of x1, x2, x3 anymore, but other than that, it's equivalent to the original system. So you can do this transformation mechanically. Okay, and the first step in our linear stability analysis is to find a fixed point. So let's find all the fixed points of this ordinary differential equation. Again, how do we do that? We just set all these derivatives to 0. So let's all these 0, 0, 0. What we get out of the first one is then that x1 is beta over 1 plus x3 power n. And that x2 is the same function, but now here we have x1. x3 is the same function, now here we have x3. So we might write this as an f of x3. Just f is defined by this term. And then, of course, we have that x3 is the same function of x2. Then x2 itself is again the same function due to symmetry of x1. So this gives us one equation that has to be true if we're finding a fixed point for the x1 component of our system, and by symmetry also for the others, which is that x1 at the fixed point is f of x1 at this fixed point. Let's write an asterisk here to denote that this is the fixed point. Okay, now how many of these can we have? How many solutions? I'm proposing to you that there's only one. And why is that? F is decreasing. Okay, so it's monotonically decreasing, only ever going down. That means that F applied to F is increasing. And that means that F applied to F applied after F is again decreasing. So then we have here two different sides. So the left-hand side is clearly increasing in x1 asterisk, and the right-hand side is clearly decreasing. So there can be only one point where they meet. There's only one x1 asterisk. And by symmetry, this is the same for all three of them. Let's call this x0. Okay. Only one fixed point. Its coordinates are x0, x0, x0. So what about the Jacobian around this point? So what we need to do here is to do d, oh, that's not the same f here. Let's say d beta over 1 plus x3n, which is the first function in our differential equation, minus x1. Let's derive this with respect to the different xi's. So x1, x2, x3. So if we're deriving this term with respect to x1, this disappears because it doesn't depend on x1. So we only have minus 1. If we're doing it with respect to x2, nothing here depends on x2, so it's 0. And if we're doing it with respect to x3, now this is the most difficult part, but it's not that difficult. Kind of we can apply the chain rule here. So we have the inner derivative of this, which is n times x3 power n minus 1 divided by the denominator squared. And there's a minus here and a beta still. So this is the inner derivative. This is the outer derivative. So like this, power minus 1. So we have the minus 1 here and power minus 2 left. So this is just some term. And we know that at the fixed point, that these here are all equal to x0. And so we can just give this a different name, and we will call the whole thing here, or let's say without the minus, because this is a positive number. Let's call this A. Okay. Whatever this is, we will look into this in a second, but first, it's just something. So the structure of our Jacobian is kind of simple. It, of course, has to be a 3 by 3 matrix. Our ODE has 3 components and 3 variables. So our Jacobian around our fixed point is of this form. So in the diagonal, we have minus 1s. It's this. Here we have 0, minus A, minus A, 0, 0, minus A. Okay. A is kind of complicated, but let's just write it like this for the time being. No, 0 is an A. Okay, now we determine, of course, the eigenvalues, so which is just the determinant of j minus lambda I. And here this is kind of not too difficult to do. If you know, like the determinant of a 3 by 3 matrix is like you take these 3 diagonals, multiply together, plus, and then these 3 diagonals multiply together, and you put a minus there. So in our case, this, and sorry, and solve 0 equal to the determinant here. So in our case, this will be minus 1 plus lambda plus lambda squared plus a squared minus a3. All this thing has to be 0. This just comes down to 1 plus lambda power 3 being minus a power 3. Okay. You can do this by hand or by computer algebra system. And that means, of course, that 1 plus lambda here is the third roots of unity. And of course, this is plural times minus 1 of minus 1. Sorry, the third roots of minus 1 times a. Okay. And of course, these are 3 of them. If we look into the complex plane, so this is minus 1. So minus 1 is its own third root, but there are 2 others, this here and this here. The key you have to multiply this 3 times this angle, you get there, and here the same. And in explicit terms, what you get so we get 1 real value and 2 complex values. 3 solutions to this equation. Lambda 1 is minus 1 minus a. Lambda 2 and lambda 3. They have to be complex conjugates of each other. And it's minus 1 plus a over 2. 1 plus I square root 3. And the other one just has a minus here. Okay? So, if you remember what we need for maybe the existence of a limit cycle, if we're lucky, is we need to have the dominant eigenvalues, so the ones with the largest real part, and they will be lambda 2 and lambda 3, because this is very negative. This is the only one that has the possibility of a positive real eigenvalue. It depends whether this eigenvalue really is positive. In this case, there is a chance of there being a limit cycle for this, which means that kind of this here, which is the real part of lambda 2 and lambda 3, would need to be positive. Then we have a chance. Then we have the local oscillations, but they don't come crashing down onto the fixed point, but they push outwards. So let's look at what is needed for this to be bigger than 2. Now, of course, we have to go back to the equation, or to the defining equation for A. So we do need A bigger than 2. That's when this thing is positive. Okay, so what does this mean? It means that nx0 n minus 1 beta divided by 1 plus x0 n squared is bigger than 2. Yep. And you can do some simplifications here. In particular, you can note, and I should have noted this 2 minutes earlier, but I can do this now. Let's do this here. Yes, we can look at the beta at the value here. Yes, so it turns out that you need to have beta equal to x0 divided by 1 plus x0 power n. Times 1 plus x0 power n, which simplifies here in the sense that we can create this beta to add a power here and to reduce 1 power in the denominator. Okay, so we have this, and here what we see in particular is that this term can only ever be at most 1, strictly smaller than 1 in particular, which means that n has to be bigger than 2. So this cooperativity constant has to be bigger than 2. And then going back, so we do know that then that x0n has to be bigger than 2 divided by n minus 2 here, just by following this argument. And it also means that beta, now we can put back in beta, that this has to be bigger than n over 2. It's kind of an unwieldy term, but we'll explore it in a bit. N divided by n minus 2 to the power of n minus 1 by n. Okay. So what all this algebra means is that we now have two inequalities for n and for beta, where we might have a limit cycle, where we might have a robust oscillation. It also means that you might have robust oscillation if you can pump up n, so the cooperativity constant, or if you can pump up beta. And actually there's, like, you can trade one against the other. If you look at the n beta plane here, it turns out that this function is like just a decreasing function in n, or something like this. And of course it starts only at 2. The possibility range of n starts at 2. But if you're above it, like, there is a given beta that is sufficient. And this is a decreasing function. That means that kind of if you have an even higher n, you can get away with a bit lower beta. So here would be the possibility range of oscillations for our system. High n, high beta, but you can trade them against each other a bit. So what that means, biologically, this beta is kind of related to the strength of the promoter. If you can have a very strong promoter, that helps you. But you absolutely need to have a cooperativity, like a steepness of your switching behavior that's as high as you can get it. And like, it pays off to have a higher n, to have a physically possible beta. Okay. Both n and beta should be high, but we can trade one against the other in bounds. And there you have it. If you solve these equations numerically, you see that indeed you do have a limit cycle. And even experimentally, this has been proven to work. Again, 25 years, like one of the first two big synthetic biology circuits was one of these. And this has been improved over the years more and more to make it more robust, and so on. Do you guys have any questions? This is unstable, but that's what we want. We want to push against the fixed point. Yes, it is, because it has been proven to work. Yeah. Or you will not have the limit cycle close to your fixed point, the unique fixed point that we identified. You just converge to it. Yeah, that's the instability. Oftentimes in control theory, you want like stability, because that goes back to a fixed point. But here we want an oscillation. So the fixed point is not what we want. We want to push out of it. Any other comments, questions? Okay, awesome. In the problem session, we have like a few, like the first one is adding mRNA to our model, to our 1D model, to see whether you can oscillate. Because now mathematically it's a 2D model, so there's not this argument that I brought before you that works to rule that out. Then we had I think we're investigating the repressilator a bit, look at the frequency, and then we're looking at the 4-gene model, whether that makes things simpler or not. Also, yeah, reminder that today we want to have the second homework. So if you have that ready, please send it to us. Next week, there's of course no lecture, so we see each other in 2 weeks. No, it's because everything here is local. The doing the derivative is a local thing, so you can't absolutely be sure. In 2D it works better than in 2D. It really works. In 3D it doesn't. You can escape a limit cycle there. You have a chance, yeah. Yeah. Cool then. Please look at the problem set. I hope you have fun with it. And yeah.
For the daylight saving times, no?
Oh yes, yes. Not for you, but for online people in France, there will be daylight savings time in 2 weeks' time. So it will be. We did the math just earlier. It's 1 hour later physically for us, depending on where you live, of course. Okay.